let us discuss Fourier transform Raman spectroscopy. Fourier transform Raman spectroscopy is one of the fastest growing areas in analytical chemistry today. Fourier transform spectroscopy uses the principle of interference to measure spectra, converting time domain data into frequency domain data through a Fourier transform, enabling simultaneous collection of spectral information over a wide range. Fourier transform Raman spectroscopy is one of the most powerful techniques for determining the secondary structure of globular proteins in aqueous solutions. It provides key information on the structure of molecules, the position and intensity of the feature in the spectrum can be used to study the molecular structure or to determine the chemical identity of the sample. Fourier transform Raman spectroscopy involves the use of multiplexing spectrometers, such as a Michelson interferometer, to detect and analyze the scattered radiation from a sample. Often, a YOG ND3+ laser is used to excite the sample so that the excitation energy is lower than the absorption band energies of organic systems. In order to eliminate fluorescence in the normal Raman spectroscopy, FT Raman spectrometer is used. Fluorescence is then minimized and the cross-section is diminished. Instruments may be combined with a microscope or optical fiber so that the scanning will be over with a few microns of surface area and Raman mapping is easily performed. FTRS consists of the following components: laser source, optical filter, Fourier transform interferometer, sample chamber, and detector. And this is the schematic diagram of Fourier transform Raman spectroscopy. So this is the laser source. The laser beam is incident on the sample, and this is the laser source, and this laser source is incident on the sample after passing through the mirror and the lens. The scattered light, so here the scattered light from the sample is collected by the parabolic collection mirror and falls on the nodes filter. So this is the nodes filter. And this nodes filter separates the specific frequency bands and avoids Rayleigh scattering. And this light passes through the Michelson interferometer. In the Michelson interferometer, the light falls on the beam splitter, and this is a beam splitter. Here the light gets partially transmitted and partially gets reflected. There are two mirrors which are used to adjust the path difference. One mirror is fixed and this mirror is fixed, and another one is movable. So at the output, there's a coherence of two light components coinciding at the beam splitter, and the resulting interference spectrum is registered. And the outcome of the Michelson interferometer light falls on the mirror and incidence on the another mirror and consequently on the parabolic mirror, and passes through dielectric filters and incidence on another parabolic mirror and incidence on these two mirrors, and the focusing mirror focus on the detector. The detector is liquid nitrogen cold germanium detector or indium gallium arsenide detector in order to obtain the signal nearer to infrared region. Then the collected data are used for the analysis of spectrum. We are going to use red or infrared laser which has sufficient energy to excite the atoms, and we can avoid fluorescence. Hence the neodymium doped yttrium aluminum garnet, rare earth element. Laser source is used in the optical arrangement. The laser beam is incident on the sample after passing through the lens. The scattering light from the sample is collected by the parabolic collection mirror and falls on the node filter. This node filter separates the specific frequency bands and avoids Rayleigh scattering. And this light then passes through the Michelson interferometer. In the Michelson interferometer, the light falls on the beam splitter. Here the light gets partially transmitted and partially gets reflected. There are two mirrors which are used to adjust the path difference. One mirror is fixed and the another one is movable. There is a coherence of two light components coinciding at the beam splitter, and the resulting interference spectrum is registered. Now the reflected light from the mirror is collected by the detector. Raman spectra of a sample are reported in the FT Raman spectrometer in the region 4000 to 100 per centimeter. The detector is liquid nitrogen hold germanium detector or indium gallium arsenide detector in order to obtain the signal nearer to infrared region. Then the collected data are used for the analysis of a spectrum. Fourier transform spectroscopy uses the principle of interference to measure spectra, converting time domain data into frequency domain data through a Fourier transform, enabling simultaneous collection of spectral information over a wide range. FT Raman spectroscopy relies on the interference of light or other electromagnetic radiation in order to create an interferogram, that is, a signal that encodes frequency information. A mathematical process, what we call this as Fourier transform, is then applied to the interferogram to convert it into a spectrum, revealing the frequencies present in the original signal. The sample is exposed to the laser radiation and the resulting signal, which is nothing but interferogram, is then Fourier transformed to generate the Raman spectrum. It offers several advantages including high spectral resolution, broad spectral range, and high signal to noise ratio. Now we shall discuss what are the applications of FT Raman spectrum. Raman spectra of inorganic species. The Raman technique is often superior to infrared spectroscopy for investigating inorganic systems because aqueous solution can be employed. In addition, the vibrational energies of a metal ligand bonds are generally in the range of 100 to 700 per centimeter, a region of the infrared that is experimentally difficult to study. These vibrations are frequently Raman active. However, peak with del nu values in this region are readily observed. Raman studies are potentially useful sources of information concerning the composition, structure, and stability of coordination compounds. Raman spectra of organic species. Raman spectra are similar to infrared spectra that are useful for detecting the functional groups and fingerprint regions that permit the identification of specific compounds. Raman spectra yield more information about certain types of organic compounds than the infrared counterparts. Quantitative applications. Raman spectra tend to be less fletchered with a peak than infrared spectra. As a consequence, the overlap of the peak in mixtures is less and quantitative measurement are simpler. In addition, Raman sampling devices are not subjected to attack by moisture and small amounts of water in a sample. Biological applications of Raman spectroscopy. Raman spectroscopy is applied widely for the study of biological applications. The advantage of this technique includes the small sample requirement, the minimal sensitivity towards interference by water, the spectral detail, and the conformational and the environmental sensitivity. Let us discuss some more applications. It is used as structural diagnosis. It is widely used in deciding the constitution of organic compounds. It is used to identify linear and non-linear structural similarities. It is used to study the strength and nature of forces which are present in crystals. It is used to calculate the force constant moment of inertia. It is used in the studies of complex compounds, mixed molecules, and water of crystallization. It is used in the studies of structure of organic compounds and isomerism, used in the studies of amorphous states and crystalline states, and so on. Applications of FTIR and FT-Raman: pharmaceutical research, polymer analysis, lubricant formulation and fuel additives, food research, quality assurance and control, environmental and water quality analysis method, biochemical and biomedical research coating and surfactants, identification of inorganic and organic compounds, identification of components of an unknown mixture, analysis of solid, liquid and gases, remote sensing, in measurement and analysis of atmospheric spectra, solar radiation at any point on Earth, long-wave terrestrial radiation spectra, and it can also be used as on satellites to probe the space. Now let us solve the two problems on Raman spectroscopy. With an exciting radiation of wavelength 435.8 nanometer, a substance showed a Raman light at a wavelength of 452.4 nanometer. Calculate the frequency and wavelength of corresponding anti-stokes line. Frequency of the exciting radiation, nu I, which is equal to C by lambda I. We know the formula C equal to mu lambda. Use the formula. So nu I equals C divided by lambda I, and substitute the corresponding values of C, 3 in 10 power 8 meter per second, divided by your lambda is given as 435.8 nanometer. Substitute here, and this will give us the value 6.88 in 10 power 14 hertz. Now frequency of the Raman line, and this is Raman light wavelength, so we'll have to use that lambda, so which is nothing but mu r equal to C divided by lambda r, which is equal to 3 in 10 power 8 divided by 462.4 in 10 power minus 9 meter. That will give us mu r as 6.48 in 10 power 14 hertz. Now Raman shift is del nu r equal to nu I minus nu r. So just to subtract this by this, that will give us del nu r, which is equal to 0.396 in 10 power 14 hertz. Now the question is, calculate the frequency and wavelength of the corresponding anti-stokes line. So the formula for anti-stokes line, which is nothing but nu AS, which is equal to nu I plus del nu R. So which is equal to, so substitute the value of nu I and substitute the value of del nu R, and that will give us nu AS, which is equal to 7.28 in 10 power 14 hertz. Now the wavelength of anti-stokes line is given as C divided by nu AS. So substitute the value of 3 C, which is nothing but 3 in 10 power 8 divided by nu AS already we have calculated, so which is nothing but 7.28 10 power 14. So you divide this by this, that will give us lambda anti-stokes line, which is equal to 412.08 10 power minus 9 meter, 412.08 nanometer. Now let us discuss another very important problem. A radiation of wavelength 546.1 nanometer excites the substance to emit a Raman line of wavelength 538.2 nanometer. Calculate the Raman frequency and wavelength of corresponding Stokes line. So this time we are going to calculate the frequency as per the wavelength of Stokes line. Now we know that nu I equal to C divided by lambda I, and of course we know that nu I which is equal to C divided by lambda I. So 3 in 10 power 8 divided by 546.1 nanometer. So which will give us this value 5.493 in 10 power 11 hertz. And of course your nu r equal to 3 in 10 power 8 divided by 538.2 in 10 power minus 9. So which will give us 5.574 in 10 power 11 hertz. So Raman shift is nothing but nu r minus nu I. So this is the value of nu r, and this is the value of nu I. So substituting, that will give us del nu r, which is equal to 0.081 in 10 power 14 hertz. And of course, we know the frequency of the Stokes line is given as nu I minus del nu r. And we know that nu I is nothing but 5.493. So minus the del nu r is nothing but del nu r nothing but 0.081 in 10 power 14 hertz. So let us substitute and get the value for frequency of the Stokes line, which is nothing but nu s, which is equal to 5.412 in 10 power 14 hertz. I think there's a mistake here, and this value is nothing but 5.493 into 10 power 14 hertz. It is not 11 hertz, it is 14 hertz. And here also 5.574 into 10 power 14 hertz. It is not 11 hertz. Okay, 14 hertz. So we have nu s, which is equal to nu I minus del nu r, which is nothing but 5.412 into 10 power 14 hertz. So your lambda s equal to c divided by nu Stokes line, which is equal to 3 in 10 power 8 divided by 5.412 into 10 power 14, which is nothing but 554.3 nanometer. So your Stokes wavelength is nothing but 554.3 nanometer.